Hey guys, welcome back. My name is MrCaproni and I teach AP Statistics for Western Hills University High School. If you got to see the last video, we went ahead and started our chapter on confidence intervals. In particular, we were looking at proportions and how we could make a solid guess for a population proportion even though all we have is a sample. So that means if I went out and I got a sample of 100 high school students and I was able to find out what percent of them fell in a certain category, I could use that information to make a guess about all high school students based off the knowledge we got from that one sample. Okay? So today we're going to continue that discussion for day 2 of confidence intervals. In particular, we're going to be looking at 3 things. Number 1, we're going to look at the difference between certainty versus precision. When you're dealing with confidence intervals, you can either make them extremely wide or you can make them extremely small. And it gets into a battle of when you want to make things wider and when smaller, and that is the discussion of precision versus certainty. All right? Second thing we're going to be looking at is going to be the worst case scenario. What if we don't have a solid proportion from our sample? Are we still able to come up with a margin of error? Are we still able to make a prediction for the whole population? We're going to be talking about worst case scenarios and what that may look like. And the third topic we're going to be talking about today is going to be our assumptions and conditions that are needed to do a confidence interval. Look, I know that sometimes looking at the assumptions and conditions is not the most fun thing to do, but remember, we are preparing for the AP test here, so it's important that we have all of this down flat, because a lot of times in extended response questions, which is the entire AP test this year, they require us to list what those assumptions and conditions are and making sure that they are met. So, again, this is day 2 of confidence intervals. If you missed day 1, remember, you can always find my videos on YouTube. If you just search MrCaproni, you'll be able to find yesterday's was actually the 13th video. Today is day 14. So when you go on YouTube, you'll be able to search exactly what yesterday's content is so that you can catch up and understand what's going on today. With that said, I hope you guys are having a great day. Let's dive in. Day 14, confidence intervals for AP Statistics. Just some review from yesterday. When we were discussing what is a confidence interval, we were talking about the idea that essentially we're going to be taking the information from a sample. So this could be 100 students, this could be 500 students, this could be 100 people that work in the business world, or maybe it's 100 bag of chips. I don't know what we're looking at in particular, but we have some type of sample. And we're going to use the information from that sample to guess that same information about the whole population. So in particular, today and yesterday, what we were looking at is when we have a sample proportion, so that's like the probability of success. So let's say, I don't know, 50% of all bags of chips created in the world are created by Lay's potato chips, or 30% of students like the idea of sleeping in right now. That would be our p hat from the 150 students or from the 500 samples of chips we got. That would be information we gathered from our p hat. Then what we're going to do is we're going to take that p hat and try to guess the proportion for the whole population. So this would be all high school students, or maybe we're looking at only all the high school students in Ohio, or maybe we're looking at all the high school students in California. Whatever it may be, we're taking the information from the sample. So let's say 30% of those students said that they like sleeping in right now. And we're going to use that to assume that 30% of the whole population believes that same thing. Now, remember, in order for this to work, we do need certain things. For example, we can't just pick our sample to be the type of people we want. We need it to be randomized. And we're going to talk more about those conditions later on. But why does this work? Well, we know in our discussion from sampling distributions that all of this information is going to end up coming together in a sampling distribution normal curve, with the true probability of success being in the middle of that curve. And every one of our samples will have a 95% chance of falling within 2 standard deviations, all right? So when we're looking at this, we're like, okay, p hat's going to probably fall somewhere within these 2 standard deviations. So we reverse engineer it to say, okay, well, what if we know p hat? then by that same argument, we should be able to know that the probability of success of the whole population is going to fall within those same distances away, so 2 standard deviations. Now, that means that we're going to be still looking at a 95% confidence interval, and we'll actually discuss other levels tomorrow. But for right now, we're just sticking with the idea of 95%. So what happens is we have our p hat, and we find now it's not called the standard deviation because we're not dealing with our proportion. We call it the standard error, but we find out how far that standard error is going to go. All right. So basically, we take the p hat, we add that error, all right, and we subtract that error to give us a lower bound and an upper bound, and we will use that lower bound and upper bound as like a range because we know we probably have an error, but we want to make a guess for this whole population. So we know we're not perfect, so we don't give one set number. Instead, we're going to give a range of numbers, and that is called our confidence interval. So we're going to go ahead and move on to our next topic of discussing the precision versus certainty in our confidence intervals. Before we dive into certainty and precision, I do need to cover one new definition, and that is margin of error. So I put together this slide to kind of help us see the difference between, because at this point we have talked about standard deviation, we've talked about standard deviation of sampling distribution, we've talked about standard error, and now we're talking about margin of error. All of these things are tied together, so don't let it freak you out. In general, here's the connection. Our standard deviation was the average distance from the mean for each of our data points. From there, we went into our standard deviation of the sampling distribution, which we used the formula p times q divided by n, take the square root of the whole thing. That was when our normal curve was centered around p. We were not able to use standard deviation as our word for this chapter because we are not centering around p, we are centering around p hat. Therefore, we don't call it our standard deviation, we call it our standard error. All right, so that's kind of what our standard error is. Now, we then moved on to talk about wanting to be things like 95% confident, which meant that we wanted to be within 2 standard errors of p hat. That is our margin of error. It's just the number of standard errors we want to use multiplied by your standard error. So if I'm actually writing out my confidence interval, I would start with p hat, and then I would subtract the number of standard errors I would want for this situation. So in our case, 95% confidence is 2 standard errors. So I would subtract 2 times our standard error, and that gives me the margin of error. And then to get the top side of my confidence interval, we would just add that same margin of error. So I don't want this whole wording of margin of error to freak you out. That's just when we combine our standard error with the number of standard errors we want to use in our confidence interval. Not super important right now because we've only talked about 95%. But as we wrap this up, we're going to be doing other percents. So that margin of error will change based off of what percent confidence we want. So how does this pertain to certainty versus precision? Well, the margin of error and our percent of confidence are directly related. As we change one, we change the other. So if I have an option here, I have to pick between 2 things. Either I'm going to have a large margin of error and have a large amount of confidence with that, or I'm going to have a really small margin of error, which in turn will give me a small amount of confidence. So, what's more important, having a wide interval and being super confident about my answer, or having a small interval but not being so confident about my answer? In order to answer this question, let's go ahead and look at it in terms of a situation. Let's see if say my principal comes to me and says, "Hey, Mr. Caproni, what percent of our juniors do you think would be capable of taking AP mathematics their senior year?" And I come back with them and I throw, "All right, well, I can't tell you exactly how many, but I did run some tests and found out that 60% of my sample were capable of being an AP their senior year. But when I did that, my standard error ended up being 5%. All right. What does that mean? It means that I could come back to my principal and say, hey, one standard error away is going to be from 55 to 65% of students. All right. One standard error would be 55 to 65, and we know that one standard error in either direction is about a 68% confidence. All right. So I look at the principal and I say, all right, I'm 68% confident that somewhere between 55% to 65% of my juniors would be capable of taking AP next year. And I can just use that decimal, multiply it by the number of students we got, and we'd have how many we could have in AP next year. And my principal looks at me and he's like, 68% confidence. So, like, almost half the time, that's not going to be correct. And I'm going to be like, well, yeah, but I have a small range, like it's from 55 to 65. My principal may look at me like I'm silly. Like, that is not enough confidence for me to be able to make decisions for our school off of. So I say, all right, well, I can be more confident. So if I want to be more confident, my range is going to be a bit larger. So let's go 2 standard errors away. Now I can tell him that we are 95% confident in our answer. But instead of being from 55 to 65, we are now going to be from 50 to now. At this point, 50 to 70 is starting to be a bit wider of a range. I'm giving him a 20% possibility of being right, like 20% in either, well, 10% in either way, 20% total. That is a range of what percent of my students could be ready for AP. All right. That's a pretty large range. So he might start getting a little iffy on that. So if he looks at it and he's like, well, I'm happy you're 95% confident, but I'd like it to have a little bit smaller. This is where we get in the battle of certainty versus precision. Precision is going to be how small can I make that range for those numbers to be of impact for our situation. Whereas my certainty is, well, what percent confidence can I place on it? As our certainty gets larger, all right, we're going to be less and less precise. But as our certainty gets smaller, like I have a lower chance, like 68, we're capable of being extremely precise. We just happen to be wrong a lot. All right. So you really want to watch this balance. Now, if I took it even a step further and said, well, why don't we try 3 standard deviations away in either direction? We're going to be looking at somewhere between 45 to 75%. And if my principal came to me and said, hey, what percent of your kids are going to be ready for AP next year? And I said, somewhere between 45% and 75%, he's going to be like, MrCaproni, that's completely useless. I could have told you somewhere between 45 and 75%. And I'm going to be like, well, I'm really certain and confident in that answer. And he's going to be like, I don't care how confident you are. I want that range to be smaller so I can actually work with those numbers. This is the balance. You don't want that interval to be so large that the numbers no longer have meaning. I mean, if someone asked me, what's the chance of passing your class, Mr. Caproni? And I said, well, you have anywhere from a 0 to 100% chance of passing my class. They're going to be like, well, I could have told you that. And I would like, well, I just wanted to be really, really certain in my answer to you. Whereas if they ask me and I can give them like there's a 70 to 75% chance that you'll pass my class, that's much more meaningful. It has much more impact. But I may not be as certain about it. Like, I could be wrong with that because not every student is the same. This is the constant battle between certainty and precision, and there is no correct answer. This is where you got to use that critical thinking skill and decide for yourself what level truly is reasonable to use. Now, in general, for the AP test and in life, most statisticians don't use a whole bunch of off the wall percents. It's almost always one of three. They either choose 90% confident, 95% confident, or 99% confident. The problem is that 90 and 99% will not end up falling like perfectly 1, 2, or 3 standard errors away. So we're going to have to find a way to calculate what the margin of error should be for those percents, which we'll do in the next video. But just keep in mind, this choice of confidence level is completely arbitrary. And the tension between the two is a critical thinking skill that you would have to use. So that kind of wraps up our idea of certainty versus precision. It's just the constant battle in a statistician's mind of how wide should I make my interval in order to be the correct amount of confidence to be able to convince the person I'm talking to that I'm correct. The second thing that we were going to cover on our list today was worst case scenario. And what did I mean by that? So there are a lot of questions on the AP test and a lot of pollsters in life that kind of use this idea of, I don't need to know the actual proportion from my sample to be able to start telling you things like the largest margin of error I would have or the amount of confidence I would have. So how do they know that if they don't have the proportion? Well, what they do is they kind of use what they call the worst case proportion that would make their margin of error as big as it will go. All right. So, what's an example of this? Let's talk. It says in April 2011, Yale George Mason poll of 1,010 US adults asking questions about current topics report a margin of error of 3%. It is convention among pollsters to use the 95% confidence level and to report the worst case margin of error based on p equals zero point 0.5. So how did they know the margin of error? So here's what they're getting at here is we know that the margin of error is equal to how many standard errors they want. So you take the standard error and we multiply it by the number of standard errors we want to use. Because we're dealing with 95%, that means that we're going to deal here with the standard error times 2. So how do they know the answer to this? They don't have a standard error. They only gave us that they talked to 1,010 US adults, which would be our N. So they gave us an N, and somehow they know their margin of error for a 95% confidence interval. So what did they do? What they did is they said, all right, I'm going to use this formula down here, remember this is the formula for standard error. All right. They're going to use this formula for standard error to find out the worst it can go. So they know, all right, we have on the bottom here 10, 10. What is the worst case scenario that can go up here for these two numbers, for p hat and q hat? What will give us the largest margin of error possible? Because if they can report the largest margin of error, then later on they don't have to seem as bad when they're like, well, actually, we only had a margin of error of 1.5%, because that would be better information. So 3% is their worst case scenario. So what numbers up here will give us the highest possible margin of error? So let's look at this. It actually comes down here. We know that P and Q are directly related to each other, right? Because really Q is just 1 minus whatever P is, okay? So let's look at our possibilities here. If we do 0.5 times 0.5, that gives me 0.25. All right, so that's semi-large. But what if I start wiggling in either direction? Let's say instead of 0.5 for my P, I have 0.6. If I have 0.6, then Q is 0.4. And vice versa, if P was 0.4, then Q has to be 0.6. So what if we multiply those two together? We get 0.24. And you can notice that 0.24 is already lower than our 0.25. So we didn't increase anything. By moving away from the 0.5, we actually made our margin of error smaller because this number was decreasing. Then if we go even further and take a look-see at 0.7 and 0.3, or 0.3 and 0.7, we go down to 0.21. So again, it's gotten even lower. And you can continue doing scenarios like this forever and ever and ever. And you will always end up getting smaller and smaller numbers the further you get away from 0.5 and 0.5. For this reason, the worst case scenario that people will use is 0.5, 0.5. So if you do not know your actual sample proportion yet, and you still want to give your client or your boss or whatever a margin of error, you can use this worst case scenario with the number of people you will be polling and give them a margin of error based off the percent, even though you don't have your information yet. All right. Now, how did they know 3% from this? Because we haven't found anything that said 3% yet. Well, what they did is they actually go out and solve this, because this will be the highest number we will get out of any of these options. And if you go about plugging that in the calculator, square root of 0.5 times 0.5 divided by 1010, you end up getting around 0.0157 7. All right. And that's a rounded off answer because it continues on. And remember, we want to go two standard deviation or two standard errors in either direction. So we would multiply that number by 2 to get our final margin of error. And if you multiply that number by 2, you end up getting 0.031. So in other words, 3.1%. That is where their 3% is coming from. It's a rounded answer of this. So essentially what they're saying is if we use 0.5, that's the worst case scenario. If I want to be 95% confident with an N of 1010, I can guarantee that my margin of error will be 3% or less based off of this worst case scenario. So let's wrap up this video by taking a quick look at the assumptions and conditions that will make this whole idea of confidence intervals possible. First off, remember we need assumptions and conditions because just using these ideas of hypothesis testing, confidence intervals, sampling distributions on any situation in life just isn't realistic. It doesn't always work. It works when we have this normal curve. It works when we have data that is reasonably randomized. If it's not, we actually can't guarantee any of these outcomes. We want to be able to make strong assumptions, not weak ones. So we have conditions to kind of help us through that. Keep that in mind when we're doing these. You don't want to come up with conclusions that don't actually show anything because you used the wrong format to get there. So these will actually directly align with some of the assumptions and conditions that we used for our sampling distribution. In fact, I hope all of them look very familiar. There are two major ideas that we need to prove to be true. The first major idea is the independence assumption. So it says here that we need to think about whether the independence assumption is plausible. It's not one you can check by looking at the data. Instead, we check two conditions to decide. So remember, independence wasn't something you can just find. We break it down into two other things. What are those two things? The randomization condition and the 10% condition. What's the randomization condition? We want to make sure that the data that we received in our sample was found at random or generated properly from a randomized experiment. We don't want to just say some Joe Schmo went out and picked his 10 best friends and got his data from them, because those 10 friends don't represent everyone in our sample. So we need to make sure it is randomized or it was done in a proper randomized experiment. The second condition that's going to help us with independence is the 10% condition. And that's when your sample size that you used for your p hat was no more than 10% of the whole population. Once you go above 10%, it starts messing with the probabilities of certain things happening. So you never want to break that threshold. It's usually pretty easy to do because a lot of times your population size is so huge that a sample size of 10% or more of the population would be extremely hard to reach. The only time that this is really an issue is when your whole population size is extremely small. Then you need to be careful of that 10% condition. The next major big idea is the sample size assumption. And it says here that the sample needs to be large enough for us to be able to use the central limit theorem. Now, I covered the central limit theorem in a previous video, so you can always go back and look at that. But the way that we check this is by the success-fail condition, which means that we have to expect at least 10 successes and at least 10 failures. And the way that we talk about expecting 10 success or fail, we said before, was when we just did P times N and Q times N. If both of those are larger than 10, so if each one of those is larger than 10, then we pass the success fail condition. All right. So I know that looks like, well, wait, we haven't done anything with 10 successes or 10 failures, but we've seen this condition. We've done P times N, Q times N, made sure they're both above 10. That's our success fail. So this really should not be anything new. Once you check through these things, if all of these check off, you can call it a day. That is all the assumptions and conditions we need. If those all are working out, then great, we can move forward with using our confidence intervals. So that's going to wrap up our video for today. I know we were a bit in the muck and not the most exciting of lessons, but in our next video, we are going to start looking at some actual examples of finding confidence interval for 90, 95, 99% and talk about how that works. And then we're also going to take a look at the calculator and how we can plug things easily in there to help us out with some of these calculations. So I hope you were able to get something useful out of here. Remember, if you ever get lost or want to catch up on some old videos, you can always look me up on YouTube at MrCaproni. Outside of that, as usual, I hope you guys will stay fit, stay healthy, and have a wonderful day.